Let's do problem number 29 on page 163 in chapter 6. Here's the problem. It says a 1,200 kilogram car rolling on a horizontal surface has a speed of 65 kilometers per hour. When it strikes a horizontal coiled spring and is brought to rest in a distance of 2.2 meters, what is the spring stiffness constant of the spring? So given. Okay. So we've got this car. This little Tesla Model 3. Okay. And actually, what a terrible thing to do to a car. And here's the spring. And the velocity was, what was it, 95? Or 65 kilometers per hour. And it gives the mass of the car as 1,200 kilograms. And it squishes the spring in, a delta X, I'll call that 2.2 meters. Hopefully it's survivable. And we want to know let's zoom out. What's the spring constant? We use lowercase k to represent spring constant. So the way we solve this is this. This has kinetic energy. And then after it hits the spring and comes to rest, all the kinetic energy is gone. And we're just going to assume that all of it was absorbed by the spring. Now, obviously, a little tiny bit of it isn't. It's going to make a noise. There's going to be a little friction or air resistance, blah, blah, blah. But we're going to assume for this kind of a problem that's negligible. So we're going to say that the kinetic energy that we had over here is going to be equal to the elastic potential energy once it's hit that spring. So all the kinetic energy is going to be absorbed by the spring. So, well, what is kinetic energy? Well, that's 1/2 the mass times the velocity squared equals, and then this is 1/2 the spring constant times the displacement. I'll just call it x instead of delta x squared. Now, when I was looking at the way you guys solve this problem, some of you are using MGH or something like that. Now, it's a wrong kind of potential energy. That's gravitational potential energy. You want to use this because this is the energy absorbed by the spring, and this also has the unknown in it. What we're trying to find is the spring constant, K. So I can solve for K. Well, first of all, the 1/2 cancels out. And so K is going to be equal to mv squared over x squared. Oops, off screen. Well, we really need to get this to be in meters per second. So let's do that first. The velocity is 65 kilometers per hour. 1 kilometer is 1,000 meters. And 1 hour is 3,600 seconds. And that gives me what I want. So 65 times 1,000. Well, duh, that's 65,000. Wow. Okay, divided by 3,600 is 18.055 meters per second. So now I can plug in my values to solve for the spring constant. Okay. 1,200 kilograms. And then the velocity is 18.055 meters per second. We'll square that. And then we'll divide it by 2.2 squared. And let's see. So 1,200 times 18.055 squared equals, and then divide it by 2.2 squared. And I get, see, 80,822, and I'll stop there. Now let's look at the units here. We've got kilogram, we've got meters squared per second squared divided by meters squared. So that cancels that. So you could have put the spring constant K as being, well, let's round this off to 8.1 times 10 to the 4. Now you could have put kilograms per second squared, which is a really odd unit. It's not very intuitive, but it's not wrong. But remember where the spring constant comes from. The spring constant comes from Hooke's law, which says the force that a spring applies is equal to negative times spring constant x. That is, the force the spring applies is in the opposite direction as the displacement of the spring times the spring constant k. So k is equal to the force of the spring over x. I'm going to drop the negative sign, but this is units of newtons, and this is units of meters, and that's the proper use of this. Now let's check that. A newton is a kilogram meter per second squared, right? And then we're going to divide that by meters, right? Mass times acceleration, kilogram meters per second squared, that's a newton. And notice the meters cancels the meters, giving us kilograms per second squared. So I'm going to just rewrite the answer. Oh, wait. That's not what I wanted to do. I wanted to write it with the proper units. So that's newtons per meter. But I would accept either of these answers as being correct. Okay, so let's zoom all the way out. So if you hit a spring and all your kinetic energy becomes elastic potential energy, you can say, hey, my kinetic energy will turn into elastic potential energy, and then you can solve for whatever unknown there is in the problem. Okay? So if you got less than 6, don't change your score. Just leave that score there. But in red pen, tell me what you did wrong, fix it, and then tell me what you learned about physics from fixing that problem. And I'd like those corrections by the end of it. Anyway, that is all.